Hello, welcome to this lesson of our study of how to solve systems of ODEs. Okay, so here we have this system of ODE here given as this. We are supposed to classify this whole system based on the variation of the parameter alpha, okay, for all alpha belonging to real numbers. Alright, okay, so before we start, let's go ahead and learn something small about how to classify the stability of systems of ODEs, okay, especially when they are linear. So this that I'm coming to teach here is about linear systems of ODEs. Okay, by the way, if you have not subscribed to my channel, kindly subscribe, okay, so that you can support the channel as well. All right, let's start. Now if you have a system of ODE, okay, what you do is let me show you one thing. You have to, with this system, you write a coefficient matrix, okay. And so here, if I'm to write a coefficient matrix, let me clean this part and put it there. Then it will be the matrix consisting of, let's say A, let's call it A, the coefficients of the variables in all the equations, or in all of the equations. Okay, so in the first equation, coefficient of x is 0, and that of y is -1. In the second equation, coefficient of x is 10 plus alpha, that of y is alpha. So this becomes the system, the coefficient matrix. Okay, then you solve for the eigenvalues of this coefficient matrix. Okay, all right, so if the eigenvalues, depending on the values you get, that is when you be able to classify them. Okay, so the classification I've done here in a table depends on the value of the lambda, the value of or the type of your eigenvalue. Okay, so the sign of it is that negative, positive, or whatever you get. Okay, so this stability that I've written here, all of them depends on, or is based on, the lambda. Okay, let me put it here so that you know that we are talking about lambda. Okay, so we call the stability or the fixed points. Okay, I was actually supposed to take you through fixed points before, but let me use this opportunity to also talk about fixed points. Let me clear it here, very simple like that. So what you do is, first, before you can talk about the stability, you talk about the fixed point. The fixed point is where you equate these two equations, differential equations. So you call this equation 1, okay, you equate them to 0. So you have negative y equals 0, and meaning that y is actually equal to 0, and you equate this part is also equal to 0. Okay, then you solve for your y and x. All right, so if you equate the both of them to 0, you could see that here negative y equals 0 mean y is equal to 0. So if I equate the whole of this equation to 0 as well, I'll get 10 plus alpha times x plus alpha 0. That means I'll get 0, so this will be 0. Okay, so it means x is also equal to 0 for one of the first points. So the first point here will be, we said x equals 0, y equals 0, so you have x star y star, that is how you write it, equals 0 0. Okay, that is how you find the first point. Okay, so after finding the first point, your task here is to classify the first point. If this first point, how do you call it, is this first point stable or unstable? Is it asymptotically stable? Is it, like that? So we go to the table, and we said that the value of the or the sign of the eigenvalue that you will get from the system will depend, you will determine if the first point you get is stable or unstable. So if you get real values, only real solutions, okay, for your alpha, or for your lambda, okay, where lambda is eigenvalue, then it means that it is called, that point or that first point is called nodal point. Okay, it's called nodal point. You have two types of the nodal point. You have the sink and the source, nodal sink point or nodal source point. Okay, so if you have all your eigenvalues being negative, all of them, okay, let's say this system, you are dealing with a 2 by 2 matrix, so the alpha or the lambda, which is our eigenvalue, will be 2 values. So if all of them are negative, then you have nodal sink, and also it is real as well, they are real numbers. Okay, then the stability of the first point we got here, that was 0 0, will be asymptotically stable. Okay, so when all of our real numbers are negative, then you have asymptotically stable system or first point. Okay, that is the first point we calculated. But if you have real numbers and all of our eigenvalues are real numbers but positive, then we have unstable system or unstable first point. Okay, but we have something that we call the saddle point. The saddle points occur when you have one of your eigenvalue being positive and the other being negative. Okay, so I said mixed positive and negative, or mixed negative and positive, and that one too, the stability of it is unstable. Okay, now let's go ahead and look at when the eigenvalues are complex numbers. When they are complex numbers, we call them spiral points. Okay, spiral, like this spiral point. That means we are dealing with complex numbers. Okay, and with a spiral point, we have the spiral sink point and the spiral source point. Okay, so when your real part of your eigenvalue, yes, your real part of the eigenvalue being complex numbers, when the real part is, so I have real part, all of your real parts is negative, then you have asymptotically stable phase point. But when the real part is positive, you have unstable phase point. Okay, what about but with the unstable phase point of spiral source, I said that when the real part is positive, we are dealing with source, spiral source. Okay, but when the real part is negative, you have sink, and you know how to classify them. Okay, when it comes to the real part being 0, it means that our eigenvalue here is purely imaginary, something like plus or minus beta I, okay, or plus and minus ci. That's what we will get, because we are saying that the real part, all complex numbers are being written as alpha plus or minus beta I. Okay, that is how it is. But when alpha is 0, it means the real part is 0, so we have purely imaginary. This means we have what we call center. The point is called center, and then you have neutrally stable, or some books will say unstable. Okay, I hope you get this now. Alright, so we are going to use these ideas to classify the system here based on the variation of alpha. What values of alpha will make us get a stable phase point? What values of alpha would make us get unstable phase point? Okay, so let's go ahead and classify it. Now, before that, like I said, you have to write the coefficient matrix for the system, and the coefficient matrix is this. Okay, and after that, you find the eigenvalues. But before that, if you remember in our last discussion, I said that the eigenvalue, or the characteristic polynomial governing a 2 by 2 matrix, is given by alpha, or lambda squared, minus trace of a lambda plus determinant of a. And then the trace of a is just the sum of all the diagonal elements, and that is 0 plus alpha, which gives me alpha. So I have it here. And then the determinant is 0 times alpha, which is 0, minus this times this, that is negative 1 times 10 plus alpha. Okay, and that becomes 0 plus 10 plus alpha, and that will give me 10 plus alpha. Okay, so that's how come I got that as my characteristic polynomial. Okay, so now let's go ahead and talk about how we will classify this. Okay, so how the characteristic polynomial, which being in terms of lambda, so I have to, for me to find lambda, I have to equate this part to 0. Okay, then we compare this to a quadratic equation, use the formula for finding the roots of a quadratic equation to solve this. Okay, so we equate this to 0. All right, so we go ahead and then we equate it to 0, and you see that for quadratic equation, the x12, this time you're dealing with lambda, so lambda 12 is given by minus b plus or minus the square root of b squared minus 4ac over 2a, and here our a is what, 1. Okay, our a is 1, our b is minus alpha, and our c is this. So you substitute everything in, and this is what we get. Okay, all right, but before you continue, let's try to find a situation whereby the inside of the square root will be 0, because it seems we have a quadratic equation inside the square root. Okay, I hope you can simplify this. If you simplify this, is what you get. Right, okay, now if I equate this to 0 and use my calculator to solve for the roots, alpha is equal to this or this. When these two conditions happen, the square root sign will be 0. Okay, so let's go ahead and start our classification. So these are the calculations we're supposed to do before we go for the classification. Now, for unstable phase point, for what values of alpha do you think when you put here we'll get unstable phase point? First of all, we've calculated that if you put alpha equals this and this, we'll get 0. We'll get 0 in the in here in the square root sign, so we get only one part of which we don't know how to classify that. Okay, that is when we have repeated, we don't know how to classify that. But let's go ahead and see. If we want to make sure that this is unstable, then it means that probably you have to get either a saddle point or nodal source. Okay, if you remember, let's go to the table and see. Okay, nodal source is unstable. Okay, this one nodal source is unstable, and then saddle point is also unstable. When it comes to complex, we have real part being positive, unstable. Okay, like that. So let's go ahead and see. When you choose alpha to be greater than 0, okay, whenever alpha is greater than 0, what will happen? It means that always we have a positive here, so we get something like it's positive, so we get positive alpha over 2 plus or minus square root of this minus 4 alpha minus 40 over 2. Now, because of this side, okay, no matter what positive value we put here, we'll get either a mixed positive and negative, because whenever this alpha over 2 is less than whatever we'll get here, it means when you subtract, you get negative answer. Okay, but when it's greater than when you subtract, you get positive. But then when you add them, always you get positive. I hope you get it. So it means it's either we'll get mixed one or we'll get only positive. So it means that when alpha is greater than 0, then we have unstable phase points. Okay, I hope you get it. And the phase points, you know how to calculate them. So the phase point x star y star equals x star, okay, y star, that is what you represent by the phase point, equals 0, 0 is unstable when we have alpha being greater than 0. Okay, so it moves to the next one, asymptotically stable. So asymptotically stable means that you should get values that will be negative, only negative answers. Okay, so let's see. When we take alpha less than 0, it means that here we will get a negative solution here, because this will be less than 0. Okay, and then the minus of it will always be less than 0. But then what if we pick values like this, less than 0? Okay, let's pick something like this, negative 2, and see and check. So you put negative 2 in, check the positive part, because you have this over 2 plus or minus that. Okay, minus 4 alpha minus 40 over 2. We know that for every value we pick that is less than 0, whenever it is less than 0, and we have here, we are dealing with the subtraction, we don't have any problem, because for whatever value we calculate and get, always we'll get negative for this, since alpha is less than 0, because we'll get a negative answer here. This will give you a negative answer, let's say k, after evaluating everything, then minus something, so automatically we will get negative solution. It means one of the roots will always be negative. But what if we are dealing with the positive? What happens? Since this is negative, okay, and we want to get something that is making us get another negative, because we are saying that for stable we are supposed to get all the real parts. Okay, if the values are real, we should make sure that the real parts are only negatives. If the values are complex, you should make sure that the real parts are also negative. Okay, so is there any value that when I put here and add them, I will get I'll get something like positive? Let me pick negative 10 and see. So I have negative 10, or let me pick one of the, you know that if you pick the root, one of the root of alpha should be equal to 2 minus square root of 11. 2 minus square root of 2 root 11. So 2 minus 2 root 11. Let's see what we'll get. We'll get negative 4.6 something. Okay, let's put negative 5 here. Okay, and see. We have negative 5 over 2 plus or minus, or plus. And let me consider the plus, because the minus part will always give us negative. Okay, let's put our calculator on in complex, so that in case we get complex solution, it still give us a complex answer. So plus, then square root of negative 5 squared, okay, so that will be 25, okay, minus 4 into negative 5 minus 40 over 2, and this is giving me negative 1.3 something something. Okay, I hope you get it. So how about let me pick something like negative 2. Okay, if I pick negative 2, that will be negative 2 over 2, and in the bracket we get 4 minus that. Okay, you should test them, because, and that is giving me negative 1 plus square root of 7i, and we have the real part to be negative 1, so we have asymptotically stable. No problem. Let's move away from the negative 5 and see if we get something. Let's move away to negative 10 and see. Negative 10 over 2, then plus square root of negative 10 square root is 100 minus 4 into negative 10, okay, minus 40, okay, over 2, and we have 0. Wow, we have 0. It means that when alpha is equal to negative 10, we have 0. Okay, all right, let's move ahead to negative 11 and see what will happen. Okay, that is, I'm considering the positive part, because the negative part we don't have any problem, always we will get a negative answer. But when alpha is equal to 10, we have 0. It means you're supposed to, that is the addition sign, you're supposed to consider something. So I have 11 squared, then 11 here, and this is giving me positive 0.09 something. So it means for us to get asymptotically stable solutions, alpha shouldn't be only less than 0, but then it should be in a range, a certain range. Okay, remember that when we had alpha equals 10, we have what, negative 10, we had 0. So it means alpha should be within this range. Okay, is it alpha should be this, alpha should be less than 0, okay, but not equal to. So it means alpha should be greater than negative 10 and less than 0. So this range will always give us, I don't know how your lecturer or your teacher will classify this, but per my analysis, this is what I'm seeing. So if in case you see any difference or any way of classifying this, you can also drop or leave that in the comment section, and then I'll take it and also look at it. Okay, so that is it. Let's move ahead and then go to the next point for saddle point. Now for us to get saddle point, what we can do is we can, like I said, you can test. Okay, we can test for what values of this alpha does this one will give us saddle point. Now if I have alpha less than negative 10, let me consider this and see something like negative 11. Okay, negative 11 over 2. Okay, let me try that. Let me consider the negative part, minus square root of negative 11 squared, and the same as 11 squared, minus 4 into negative 11. Okay, then minus 40, okay, over 2, and this is giving me negative 11 point something. So when I consider something less than negative 10, I had this. Okay, let me consider the plus part and see. So this was the answer I had was with the negative part. Okay, so when you consider the positive part, I'm getting 0.09 something. It means that whenever alpha is this less than negative 10, I have saddle points. Okay, now let's consider another case. When alpha is bigger, let's consider something. We know that when alpha is equal to, one of the roots of alpha was 2 plus 2 root 11. When alpha is this side will be 0, and we'll be getting only alpha over 2. Okay, so let's consider values greater than that, 2 root 11, 2 plus 2, and that is 8 point something. So let's consider values like 9 and see. So you have 9 over 2, okay, plus square root of 9 squared minus 4 times 9 minus 40 over 2, and this is giving me positive something. Okay, for the plus side, when I consider the negative side, I'm getting positive again. Okay, but if you consider big values, okay, big values of alpha, you'll be getting saddle point. So if you want to continue this, you can actually continue and say that for bigger values of this is what you get. Okay, for bigger values, you can consider your own bigger values, but then let me see, I want to make sure that all the bigger values I've chosen are the same. Alright, so for bigger values of alpha, you have the subtraction part, you get minus, and then for addition parts, especially I'm talking about positive values. Okay, for addition parts you get minus as well. Sorry, for let me take that point again. For bigger values of alpha, as in when alpha is equal to infinity, okay, positive infinity, let me put it that way. When you are taking bigger values, you'll be getting alpha 1, 2. One of them will be greater than 0 and the other will be less than 0, so you get saddle point. So per my analysis right now, the analysis we've done right now, if you pick values, we said that for saddle point, alpha is less than -10. If you pick values less than -10, which is -11 downwards, you get the subtraction part will be negative, but the addition part will be positive. Okay, so it means that you'll be getting addition and positive, which is saddle point, and alpha equals positive infinity, and that one too will give us saddle point, because in the subtraction part, like I said, you get negative, and in the addition part you get positive. Okay, that is my analysis. So you can sit down also analyze this, and maybe you can come out with a different solution as well. Okay, but mind you, your alpha should be in the real numbers. Okay, all right, so you have this for spurious points. Okay, the question is, for what values of alpha should I pick so that I'll get complex number, because we are talking about spurious point talks about complex numbers. Okay, so it means that I should choose 2 minus 2 root 11. I'm writing something and then you understand. For if I pick the roots of alpha and put them here, I'll get 0. Okay, but let me consider the range between these. So this 2 minus 2 roots 11 is giving us -4.6 something. Let me say -4.63 less than alpha less than 8 point something. Okay, this is 8 point something. Okay, 8 point, let's say 63. Okay, pick values within this range. Okay, when alpha is equal to 0, what do I have? Something else. Okay, it means that alpha cannot be equal to 0. When alpha is equal to 0, this part will be 0. Okay, so it means we'll get purely imaginary, and you don't want that as well. So it means that for us to get a spurious point, we have two ways to consider them. Okay, let's pick values like this is -4 point something. Okay, this is 8 point something. Okay, so let's pick values like -3 and see. When I pick -3, let me consider the square root side, because that is what we want to get complex numbers from. Okay, 3 then -40. Yes, when you consider -3, it means that when I pick negative numbers and I want to consider them, it should be this. The range where we'll get spurious points will be this. With the first, this is the first one, or 0 less than alpha less than 2 plus 2 root 11. Sorry, and this you can take like something like 8. Okay, so square root of 8 squared minus 4 into 8 minus 40, and this is giving 2 root 2i. So it means that for me to get spurious points, I should consider these two ranges, this or this. Okay, and this will work for my alpha. Okay, so let's consider other points for nodal points. Okay, for us to get nodal points, it means that we should get only real numbers. So for us to get nodal points, Okay, for us to get nodal points, where is my solution? We said that alpha should be 1, alpha should be greater than 2 plus 2 root 11, or alpha should be less than 2 minus 2 root 11. Okay, these are the two ranges that alpha will always be a real. When you put alpha to be these in these ranges or in this range, then it means we'll get our solution lambda 1 2 to always be real numbers. Okay, now let's go ahead and classify nodal sink. For us to get a nodal sink, okay, nodal sink, it means that we should get node, but then the solutions should be only negatives. Okay, and if you remember, I said something like this with a saddle point. I said always when alpha is less than here negative 10, okay, you get a plus side to be positive and the subtraction side, is it no, the plus side to be, yeah, something like that. You get positive and negative. Okay, but if you only want to get negatives only, real numbers, that means alpha should be within this range. Nodal sink, so you should get negative 10 less than alpha less than 2 minus 2 root 11, because nodal sink means that we should get real numbers and then all of them should be negative. Okay, so if I pick values like negative 9, it is within this range, so I have negative 9 over 2. First, let's consider the addition part. Square root of negative 9 squared minus the negative 9 squared. You are squaring all the negatives, so it's negative 9 all squared minus 4 into negative 9, okay, minus 40 over 2. Okay, and when I consider the addition sign, I'm getting negative something, negative 0.111. When I consider the subtraction part, automatically I'll have to get a negative answer. Okay, so like that, I have negative 8 point something something. So it means that for us to get nodal sink, this is the solution, the range for alpha values. Okay, let's go ahead and find nodal source. For us to get nodal source, it means that we should get only positive values. Okay, only positive values, and for that matter we are supposed to get something like alpha being greater than 2 plus 2 root 2 root 11. Okay, at some point it will change, though. That is when you get bigger values, but then this is okay. We don't know the exact point. That I don't know, I've not done that, but if you can check that for me, that would be very, very nice. Okay, so at some point this will change to saddle point. When it's greater than, it means values bigger than this, and as we are going higher, you reach the infinity zone, it will be changing to saddle node. But then let's put it this way, that for us to get nodal source, alpha should be greater than this. Okay, I hope you get this. All right, let's move ahead. For center, it means you are supposed to get purely imaginary. Okay, so let's consider when alpha is equal to 0. It means I have lambda 1 2 being equal to alpha over 0 is 0 over 2 is 0, so I have plus or minus square root of alpha is 0, so negative 40 over 2. So I'll get a purely imaginary this thing, negative 40, and that is plus or minus 2 root 10 I, okay, over 2. That will give me plus or minus root 10 I. Okay, so when alpha is equal to 0, if you write this in exams and maybe your lecturer or your teacher marks you wrong, I don't know, but you should go and then ask him. Just sit down with him and then analyze the thing. Maybe he might have made a mistake or something like that. Okay, so just go ahead, and this is the solution for center. It means we are supposed to get purely imaginary from the table we had and discussed earlier. This is what we said. We said that for us to get center, it should be purely imaginary. Okay, now let's go to spiral sink. Spiral sink means that my real part should be what? Negative. Okay, so let me see. Spiral sink, my eigenvalues should be what? That is the real part of my eigenvalues should be only how do I call it, they should be only the real part of my eigenvalues should be one. First of all, okay, let me talk about the sphere. The sphere should be complex and the real part should be negative. Okay, so it means that I should get this range. Okay, we've already done this. We said that, if you remember here, the sphere source, as I said something like where is the sphere nodal point? Okay, sphere point, this is what I said this or this. Okay, so if you consider this part, okay, the first part, the first range, this one, you see that you'll be getting the real part to be only negatives. Okay, you'll be taking negative alphas. Okay, I hope you get it. So for sphere source, sphere sink, the range should be 2 minus 2 root 11. Okay, is it 2 or negative? It's 2, right? I hope you solve for the roots. Should be less than alpha than less than 0. This range will always give us sphere sink. Okay, now let's go ahead for sphere source, and that one too should be 0 less than alpha less than 2 plus 2 root 11. And all of these, every number within this range, okay, this is 8 point something, this is 0, so within the range of this, okay, 8.6 something, so you can pick 1, and 1 will give you positive real part of the complex numbers, because you get 1 over 2 plus or minus something, and always these will be positives. Okay, I hope you get it. So now let's go ahead and then I think that is all. Right, that is all for our discussion. So if you remember, you can go ahead and look at the question and the table again. This is a question and this is how the table works. So you can look at this table, you can take a picture of it, you can pause it and then go through it and use it to solve this question, okay, using your alpha. All right, thank you, and don't forget to subscribe to my channel. See